with this picture, with the route of blood flow to the heart, that we put it in sequence. 1, 2, 3, 4, 5, 6, 7, 8, like that. All right, so you would think blood is going to go to the right atrium, then to the right ventricle, then to the pulmonary trunk, then to the lungs, then go back to the left atrium, and then left ventricle. All right, no, that's not how it goes, right? Because that becomes inefficient. Now, this is a good way of finding the sequence, right? So if I was a red blood cell, then I would go through this in sequence. But keep in mind, right? And I want you to think about this. This occurs in the right side as this occurs on the left side. So as blood goes into the right atrium from your body, blood returns from your lungs into the left atrium. As blood goes from the right atrium to the right ventricle, blood is going to go from the left atrium to the left ventricle, right? So this is happening concurrently at the same time. So at the same time, we have 1, 2, and 3, we have 5, 6, and 7, right? It's happening at the same time. So as the blood is going into this, coming back from our body into the right atrium, blood is coming from the lungs, entering the left atrium. Then that blood goes into the right ventricle, blood goes into the left ventricle. As you contract the heart, now there's blood in both sides. If it goes in sequence, what happens? You contract the right ventricle, then then you bring it to the lungs. At the same time, you have to wait for the left ventricle to contract, right? That kind of doesn't make sense if we kind of read it in sequence here. What I want you to do is cut it in half, right? What happens here happens at the same time here, right? Then it kind of makes sense. As you eject blood from the right ventricle into the pulmonary trunk, you will be ejecting blood from the left ventricle into the aorta, right? That makes a lot more sense. As blood goes into the lungs, blood is going to go into the aorta, into your body. So it happens, all right, at the same time. And that's the big picture thing I want you to understand, is that it makes it easier, we kind of talk about it in sequence, but it doesn't make sense, all right? So I want you to think that as this is happening here, this is happening on the other side. Perfect, right? And we'll talk about those sequence and the cardiac cycle in a second.
Does they happen at the same time?
Yep, all of this happen at the same time, right? So it happens concurrently at the same time. Now, it kind of makes sense because if it isn't happening, then the right ventricle contracts and ejects blood, and the left side doesn't do anything yet. It has to wait for that blood to come back, and then it can contract, right? Well, that's very inefficient then. Right. Oh, last couple things. I'll go through this, I like. Right? So the semilunar valves right here, right? That's an opening to the right and the left coronary artery. These valves open and close. They open at ventricular contraction. Now, ventricular contraction is called systole. You will hear that, systole. You will hear the book talk about atrial systole. We don't really consider it, systole, because the contraction of the heart, right, is more dependent on the ventricles. Ventricular relaxation is diastole. So systole is an active contraction of the ventricles, which will then eject blood. Diastole is a relaxation of the ventricles. So systolic blood pressure measures your contraction strength of the left ventricle at contraction, right? And you would think diastole is your blood pressure at rest. But we're going to see the blood pressure of your left and your right ventricle at rest is almost 0. So that's not our diastolic blood pressure. Right, the last thing I'll talk about, and then I'll give you guys a break, is this one, right? Histology right here. And I want to, all right, this is the fibrous skeleton. This is not your pericardium. Obviously, I wrote that because I had a lot of test questions and people were describing the pericardium. Right? The pericardium is external. It's found outside the heart. The fibrous skeleton is found as part of the internal structure of the heart. The fibrous skeleton are plates of connective tissue. So these are plates we're talking about. These plates of connective tissue cause three separate important functions. The first one, these are fibrous rings that help support your valves. Think about your aortic valve. Your aortic valve has to withstand pressurized blood from the left ventricle with each ejection, right? And we're gonna see, you're gonna have what? At least 60 beats a minute, for every hour, for every day of your life. And if it rips, we have an issue. So that valve needs to be incredibly strong. It can't fail. If it fails, immediately we have a real big issue, right? Like immediate surgery and replacement of the valve. So in terms of the histology and the fibrous skeleton, right, providing support to the valves might not sound important, but it's what allows us to survive. The next one provides electrical insulation between the atria and the ventricles. Notice that these are all found between the areas of the atrium, and it's found between the atrium and the ventricles. What happens is this, right? When we electrically stimulate the atria, we only want the atria to contract, right? We don't want the ventricles to contract at the same time. So some way, we need to kind of disconnect those two areas. So then I can only stimulate the atria and only the atria contract. This is how we do it, right? We have a pacemaker that stimulates the atria. So then the atria contract. Then the signal then pauses, right? As it pauses, that electrical signal doesn't go to the ventricles right away. It allows the ventricles to be disconnected from the atria, allowing us to stimulate the atria first. As the atria stimulate and contract, then we stimulate the ventricles. Atria first, then the ventricles, right? It allows those two separate timing of the contractions. So then you don't have all four chambers contract at the same time, which will be bad, obviously, right? Now the last one, if you take a look at it, cardiac muscles are very similar to skeletal muscles. They have the same arrangement of proteins, right? And skeletal muscles, you need to anchor it in place. You have an origin and an insertion, right? So you have the origin where the actual skeletal muscle is anchored, and an insertion where it's pulling. Well, the heart doesn't really have any bone matter to provide some kind of resistance. So you don't have any anchoring point, no bone here. But we do have this fibrous skeleton, right? This thick plate of connective tissue allows you to anchor and insert. So then you can create tension. Now if you take a look at this right here, notice that these are in rings right here. And then this one is kind of up in a ring as well. So all muscles, when they contract, they shorten. So as these guys shorten, they shorten and squeeze. As they shorten and squeeze, they shorten and squeeze from the bottom up. So then you can eject blood out of the superior part of the heart where your great vessels are found. Perfect. All right, we'll stop right here and take a little break.